Okay guys, in this last video, which is probably with respect to modeling using growth and decay, exponential growth and decay, is probably the most important video because we're going to talk about how we often use continuously compounding interest equation, that equation, to model the growth or decay of a quantity over time. And so first things first, we're going to look at this model you see right here. It says y equals AE to the RT. Now I'm going to write this model another way. I'm going to write this as A equals PE to the RT. But what I want you really to understand is that these two models kind of say the same thing. As a matter of fact, I'm going to write it one more time. And we're going to say AE to the Rx, okay? And so generally speaking, when we look at continuous growth models, we have our natural base as a base of our exponent. And when we looked at this with finance, we said that the amount at a given time t is equal to what I started with times e to the rate times time. So when we look at these models, some things we want to acknowledge are these. We say y, or f of x, or a here, is going to represent the amount remaining at a given time t, where t is the time, in this case, is the time. But I say it's usually but not always expressed in years. So with respect to the models we tend to look at, we look at years a lot of the time, but I want you to know that t is our independent variable here, and we can just as easily use x in its place. Now the two, I guess, bits of information that I would ever need to know in a continuous growth type of situation are, what am I starting with here? So I say A is the initial amount of something. I suppose I mean this A right here, and that kind of parallels the fact that we said that that was our principal amount at time 0 when we talked about finance. And then we're going to say R is the rate of growth or decay, of course, and it must be written as a decimal. Now, some things. If you are modeling growth, then we know that this exponent up here is going to need to be a positive rate, okay, or a positive exponent. So a good way to remember this is when you think back to your parent functions, y equals b to the x, if this was a positive up here, then you got this nice growth curve look like this, okay? But if I were to do something like y equals b to the negative x, where we have this reflection over the y-axis, this would mean that in this sense I have a negative rate, and we would get something that is decaying over time. So looking at this, it says if the rate is positive, then we're going to represent exponential growth. If the rate is negative, it's going to represent decay. So how do I know if it's positive or negative? Well, usually they're going to tell you that the rate is some percentage, but then they're going to use the words like decaying or growing, and you're going to have to assess the situation. Should I put a plus or a minus on this rate, depending upon what it's doing here? So looking at how this model actually comes into play, this is a really good example of how you might see a model be used to represent change in something over time, especially with, say, population. So this example reads, the projected population of the USA for the years 2020 through 2050 can be modeled by P, or P is our population, in millions, and this expression here, 290.323 e to the 0.0083 t, that represents the t there, our time in years. Now, something that tends to get done quite a bit when we use times in years is this. If I wanted to say, use this model to go find out the population in the year 2020, a really bad thing to do would be to substitute 2020 for your time, because that, excuse me, would be like saying, I want my initial population to compound 2020 times. So that is to say that if you say that time is 2020, you're saying 2020 years after the very, very first year. So what we do is we tend to index this, and we say things like, well, let's let t equal 20 correspond to 2020. So that means that if I were to say, well, what is t equals 0, the initial time, that would have corresponded to the year 2000. And we just kind of start by saying we need to declare when's our first year going to be. And that doesn't mean we have to come out and say t equals 0 is 2000. We could just simply say t equals 20 is 2020, so the year 0 is inferred to be the year 2000. So looking at our model here, let's kind of pick it apart. I knew that this value out in front here, I was told that this is my initial value. So if our population in millions has this initial value here, it's kind of like saying that in the year 2000, they would have started with a population of 290.323 million people. And with respect to is it growing or decaying, I suppose we could just look up here at our rate, and I notice that our rate is positive. So we have a growth situation here. So in terms of does this model represent growth or decay and what is the rate, I see that my rate in this case is positive. So we have growth. And so I would say this is a growth situation because the rate is positive. At the same time, we want to identify the rate. So I'm going to write the rate is 0.0083, and I'm also going to write this as 0.83%. This is the one that's most important to me, but I do want you to keep in mind that if you scooch that decimal twice back to the right, we're saying that on an annual basis, it's growing at about almost a full percentage every year, about 0.83%. So we know that we have growth here. What I want to do is determine what's the population of the USA in the year 2000. So you might go, well, didn't we already talk about this? But I do want to kind of consider this again. What year would be 2000? Well, that'd be year 0. So anytime I'm given a model, what I'm going to do is I'm going to say, well, if you're asking me for population, you're giving me a time, I'm going to go plug in that time value, and I'm going to go solve for population. So 323 e to the 0.0083 times 0. So because this is a 0 up here, 0.0083 times 0 is 0, and this leads us to 290.323 e to the 0, which is the same thing as, remember anything to the 0 is 1, is the same thing as this times 1. I want to fix that 3. It's bugging me. Times 1, which really means that our initial population would have been our principal amount that was located in the front of this model here. Now, what we're going to do for the remainder of this problem is look at how we can use a graphing utility to our advantage when we work with these. So this is going to be a little bit of practice on how you model something on your calculator. So I want you guys to go to y equals on your calculator, and what we're going to do is model this for the years 2020 through 2025. So first things first, let's put in our model and know that we don't have p equals, we can only do y equals, and we can only use x's and not t's. So when we type this in, we say 290.323 e to the power of, and we're going to say 0.0083x. And we have to put an end parenthesis on this because all of that 0.0083 times x is all up in our exponent. So now, if I hit graph at this moment, what you're going to see is not a whole lot. And the reason why is just because if I'm reading this as my x-axis is time and my y-axis is population, what I know is if I even were to make a table of this, which we can do, if I go second graph, you're going to see that at year 0 we're already at a height of that 290.323, and it's only going to get bigger. And to top things off, we only wanted to look at this from the years 2020 through 2050. So what we are going to do is this. We are going to use a graphing utility to graph the function from 2020 to 2050 by going to window. And so we need to stop and think about this critically. Starting with x min and x max, this is kind of like saying, what do you want your first time to be and what do you want your last time to be? Now, I wanted to represent this from 2020 to 2050, and if t equals 20 is 2020, then what I'm going to do is I'm going to make my x min 20, and I'm going to make my x max 50. If I am going from 2020 to 2050, maybe I don't want to go by 1-year increments, so it might be easier to go by half decades, like every 5 years on your scale, or every 10 years, but I'll put in a 5 just to humor myself here. Now in terms of my y min, I'm going to make it negative, even though I don't ever have a negative population, but it just means that it'll be easier to see our x-axis when we graph this here. But as far as y max goes, well, hey man, I'll tell you, we're starting at 290.323 and it's only going to get bigger. So I say go big or go home. I'm going to go up to 500 million people, and if I'm going from 0 to 500, then maybe I want to go by 100s. One thing to keep in mind is if you're ever going up to say 500, think about how would you go from 0 to 5? Would you go by 10s? No. 0 to 5 you'd go by 1s. So from 0 to 5 you would make a scale of 1s, then 0 to 500 you would go by 100. Okay, we just put that suffix on the end of this. So if I hit graph now, what I'm going to see is this growth of my population over time. And to put this into context, I would say here's the year 2020. If we hit trace, okay, and I hit 20, enter, it's going to skip over here and say at the year 2020 you had about 342.75 million people. And then we could kind of just scroll along here and say at a given year, approximately what does this model say we will have in millions of people, okay? So now that we have this on our graph, it's kind of like using our graph to our advantage. Part D says use the table feature of the graphing utility to create a table of values for the same time period as in Part C. So you notice I did go to table earlier, And table's a lot like graph in that it's run off this function that we put in here. So in order to look at the table, I have to hit second graph. And what you see is in the year the year 0, this would be the year 2000. What we wanted to do was look at the ranges of years from 2020 to 2050. So just like we adjust our graphing window by going to Window, if you go to second window, behind this it says Table Set, and it's going to ask us two questions. One, what year do you want to start your table in? So if I want 2020 through 2050, I'm going to start 20 years after 2000. And if I'm doing this, maybe I go by like 2-year increments just to take a look at what this table would look like. It would just start at the year 2020 and it would go by 2-year increments here. You can change your delta table at any time, and that's just kind of like what do you want your difference in your x values to be. It's kind of like saying your scale. So I'm going to set this back to 1 just because I really like going by ones on my table. But you can see that 2020 through 2050, I could just simply scroll down here from the years 20 to 50 here to represent the years 2020 through 2050, and I would have a good idea of what our population's doing within this time period. So for parts E and F, we're going to use our model. And so it says use your model to find the population of the USA in 2025 and in 2040. Because we've already made a table, all I have to do is go back to the 25th year here and say in 2025, what is my value? And so I see here that it's about 357.27. I'm just going to go ahead and make sure that I transfer this over to here. So we got 357.27 as our population. So our population was given as P as a function of time. And this was 25 years after 2020. Now 40 years afterwards, we can go back to our calculator again and just go evaluate at the 40th year here. Look at our table, 404.64 million people. Okay. So with respect to these values you see here, it's nice if you already have a table. What if you don't have a table? Hey, you know what? We had a model. Our model was 292.323. So I can say 292.323 e to the power of 0.008. And I suppose we have 83. And this would be times the time, which is 25 years. You see that we get the same value that we had gotten before. 25, what is that? I typed this in incorrectly. 292.323. We have e to the 0.0083 times 25. We got this right here. So if I go look at my table, it should be the same thing. Did I look at the wrong entry? 25. 357.27. And when we evaluate this here, 292, that's what happened. You guys, I typed 292. It's 290.323. There's this value we got on our table. So just know that you don't have to put this in for y equals and make a table to tell me these things. We can just say I'm looking for a population at a given time. Let's substitute in the time to our model here, and we'll solve for the population. Now this is a good question right here. According to the model, during which year will the population of the USA exceed 400 million people? Now this is kind of like saying, if I know I want my population to be 400 million people, we can plug in 400 for our population, and what we're really trying to do then is work backwards to solve for, man, what the heck would my time have to be? The unfortunate thing for you is we haven't talked about logarithms yet. So we don't really have an algebraic way to solve for this, but with our graphing calculator, it is something that if I go look at the graph here, I say, well, when does this get to a population of about 400 million people? And so I know on my y-axis here, I went up to 500 million people by 100 millions at a time. So, excuse me, if you were to trace out here, 400 million people would hit your graph right about here, and trace it down. These were in increments of 5 starting at 2020. So about right here would be 2025, 2030. 2035, a little, maybe like 2037, okay? How could I do a better job? We could go look at the table and say, now looking at your y column, where does it get really close to 400? And we said specifically surpass 400. And so at this point I could say, well, you know what happened beyond 38, but somewhere before 39, somewhere between the 38th and 39th year, we will surpass 400,000. So to answer this question for right now, I would say that T must be between 38 and 39. And I'm not going to include 38 and 39, but we could narrow it down. So to answer this question right here, we could say that the population of USA will exceed 400 million people somewhere between the years of 2038 and 2039. So just because you're getting me time values when we read our calculator doesn't mean you don't have to answer the question in what years will this happen. Okay? Cheers.